We know that it's not an easy task to study and analyze the planets and moons of our own solar system, as they are millions of kilometers away from Earth. However, exoplanets are not just millions of kilometers away, but many light years away from Earth. How can astronomers manage to study exoplanets if they are trillions of kilometers away? There are several methods used by astronomers and astrobiologists to discover and to study these extremely distant, mysterious worlds. Before the launching of the Kepler mission in 2009, the most successful technique for detecting exoplanets was the Doppler spectroscopy, also known as the radial velocity method. The radial velocity method relies on the fact that a star does not remain completely stationary when it is orbited by a planet. A planet is much smaller than its star, but it still exerts a tiny gravitational pull or tug on the star as it orbits. When a planet is behind the star, from our point of view, it pulls the star slightly away from us. When it's in front, it pulls the star slightly toward us. This causes the star to wobble back and forth. Astronomers look for this wobbling to find planets. They use something called a spectrograph and powerful telescopes to examine the light coming from a star. A spectrograph, like a prism, splits the light from the star into its component colors, producing a spectrum. Some of the starlight gets absorbed as it passes through the star's atmosphere, and this produces small, dark gaps or lines in the spectrum. As the star moves closer to us, these lines shift toward the blue end of the spectrum. As the star moves away, the lines shift back toward the red end of the spectrum. So the spectrum appears first slightly blue shifted and then slightly red shifted. Therefore, astronomers can look for orbiting planets by looking for these back and forth motions of the lines in a star's spectrum.
And you can work out from the speed that's being pulled towards you and how long it takes to go around in that circle, you can work out the mass of the planet or the companion thing which is pulling it around. If that mass is very small, the thing is a planet. That method has been very successful. It found most of the planets which were discovered early on.
However, the Kepler technique was based on the planet's transit. The transit method is based on the observation of a star's small drop in brightness that occurs when the orbit of one of the star's planets passes. Transits in front of the star. The amount of light lost depends on the sizes of the star and the planet, and the duration of the transit depends on the planet's distance from the star and the star's mass.
With the Kepler Space Telescope, when we look at a star, we don't see the planet directly. All we see is a tiny dip in the brightness of the star when the planet passes in front of it. From the size of the dip, we can work out the relative size of the planet. Is it a big planet or is it a small planet?
The combination of transit photometry and Doppler velocimetry reveals planetary radius, mass, and density, which are some of the main parameters to evaluate the potentiality of the exoplanet as an Earth-like candidate, and so to harbor life.
Once you know the distance away from the star and you know how hot the star is, you can estimate what the temperature on the surface of the planet would be like.
Another of the main parameters to analyze the Earth-like potential of an exoplanet is its atmospheric composition. Atmospheric studies of exoplanets might be performed with spectroscopy during planetary transits. During the transit, the stellar light passes through the atmospheric limb of the planet. Spectral analysis of this filtered light reveals the structure and composition of the atmosphere. Astronomers could identify the most Earth-like exoplanets by detecting the biomarkers, which are the imprints that life forms have on their host planet atmosphere. For instance, the molecular oxygen that we are breathing results from the presence of life on Earth. Unfortunately, with present-day technology, it's extremely hard to closely study the atmospheric composition of those remote planets.
The main thing that's keeping us from being able to do that now, of course, is technology. We don't have the technology in functioning instruments at the moment to be able to do that effectively. But that's something that will change with other missions in the pipeline, like Jack Webb Space Telescope and other missions that are happening.
Kepler continuously monitors over 100,000 stars similar to our Sun for brightness changes produced by planetary transits. Thanks to this ingenious technique, Kepler has confirmed to date more than 1,000 exoplanets. Scientists think that about a few dozen of them can be labeled as Earth-like. Considering the possibilities of finding an Earth-like exoplanet are much higher in the circumstellar habitable zone of its planetary system, the planet hunting then started to focus on those areas. One of the first discoveries was 70 Virginius b, an exoplanet located approximately 60 light-years away in the constellation of Virgo. 70 Virginius b was located exactly in the middle of the circumstellar habitable zone of its planetary system, so it was supposed not to be too hot or too cold. Unfortunately, further studies reported that this remote world was a gas giant with very high temperatures, which ruled out any potential for liquid water, and therefore of life. The early findings were discouraging in terms of detecting an Earth analog. But this was just the beginning. In 1998, a discovery made in the star Gliese 876, a red dwarf located in the constellation of Aquarius at a distance of 15 light-years away from Earth, really encouraged astronomers. A gas giant was detected in its habitable zone, Gliese 876b. Three years later, another gas giant closer to this one was found, Gliese 876c. We know that life as we know it is not possible on gas giant planets such as Jupiter or Saturn. But the big surprise was that both exoplanets may have habitable moons orbiting around them, as Jupiter and Saturn have.
This was one of the first planets to be discovered in the habitable zone, and people theorized that if it had a moon around it, the moon would be rocky, and the moon would be the right temperature to have liquid water.
Why couldn't any of these hypothetical moons around Gliese 876b and c harbor life, as we hope Jupiter's moon Europa or Saturn's moons Titan and Enceladus might?
So it's an exciting place to think about, and maybe an exciting place to look for in the future.
After the discovery of these exoplanets with potential Earth-like moons, several similar exoplanets with moons orbiting around them were discovered. Maybe on any of those remote moons, life arose in the past, or exists in the present, or might appear in the future. After all these early discoveries, we started to approach to the main goal, to find the most Earth-like world. An Earth analog, also referred to as a twin Earth or Earth-like planet, is a planet or moon with environmental conditions similar to those found on the planet Earth. If life could arise on Earth millions of years ago, and if we look for exoplanets similar to our planet, the chances of finding habitable planets skyrocket. Recent discoveries have uncovered planets that are believed to be similar in many ways to Earth, with relatively high Earth similarity indexes. The size is often thought to be a significant factor, as planets of Earth size are thought more likely to be terrestrial in nature and be capable of retaining an Earth-like atmosphere.
From From the point of view of Kepler, a planet is Earth-like if it's small enough that it's probably rocky. It's not a gas giant like Jupiter or Saturn.
But size alone is a poor measure, particularly in terms of habitability, because next to us, there is a planet with a very similar size and mass, Venus, where it is almost impossible for life to arise. There are other criteria to be considered, like the surface gravity or the star size and type.
A planet is Earth-like if it's the right distance away from its star that it's in the habitable zone, that it's not too close that it's too hot and all the water that it would have would boil away, and not so cold that if there was any water on it, it would all freeze to ice.
If we are able to examine all of these parameters of an exoplanet, we would be able to know if it is or not a real twin Earth.
So when we say Earth-like for Kepler, we usually just mean that it's small enough that we think that it's solid enough that you could stand on it, but that doesn't mean that it has an atmosphere or that it has an ocean.
It's also often cited that an Earth analog must be terrestrial. That is, it should possess a planetary surface composed of materials similar to Earth's. The conclusion would be that extrasolar planets, or moons, in the center of its circumstellar habitable zone, the so-called Goldilocks position, with substantial atmospheres, may possess oceans and water clouds like those on Earth. In addition to surface water, a true Earth analog would require a mix of oceans or lakes and areas not covered by water.
We believe that water is essential, but just about everything else you can think about, which is important for life, there seems to be life on the Earth that doesn't need it. There is life that survives without sunlight, there's life that survives without oxygen, there is life that survives deep down underneath the ice in Antarctica.
Unfortunately, with the present technology, we can't properly evaluate most of the parameters like the temperature, the atmospheric composition, or the surface of the exoplanets.